Welcome to today's lesson. It's an introduction to matrices. For your objectives today, students will be able to perform matrix operations such as addition, subtraction, multiplication. Students will also be able to find what's called a determinant of a square matrix and determine an inverse matrix. You should have taken a look at the activator. In your activator today, we were actually looking at a visual representation of a matrix. All right, a matrix is a set of numbers arranged in rows and columns. And it's going to be a rectangular arrangement. For example, this image here has 3 rows and it has 5 columns. We could talk about the item at position 2, 3, which would be the row 2, column 3. It would be this 10 right in the middle. So anyway, that's a visual representation of a matrix. In today's lesson, we're going to learn what is a matrix. How do we perform operations with matrices? We're going to learn about what's called the identity matrix, and we're going to learn about inverses and determinants of matrices, which help us to perform additional operations and solve other problems using matrices. So what exactly is a matrix? Well, simply put, a matrix is a rectangular array of numbers. All right, it's a way in which we arrange numbers in an array with rows and columns. All right, they provide an efficient way to solve systems of linear equations and to record data. The tables of data presented throughout the book that we've used in this course are examples of matrices. So the definition of a matrix, all right, well, if we let m and n be positive integers, then an m by n matrix, and that's how you read it, is a rectangular array of m rows and n columns of real numbers. We use what's called the shorthand notation a sub ij for this matrix. All right, and what does that I and j, what do those really represent? Well, each element or entry in the array, each number that we find in the array, is at a position where we say a sub ij. All right, this is what we call double subscript notation. The row subscript is the I, and the column subscript is j. So if I say, what is in the array at position a sub 1, 2, would just say, what's at row 1? All right, that's row 1, which is right here, and column 2, which is right here. So the element there would be this position right here. In general, the order of an m by n matrix is just m by n. So if we had an array that was, say, 3 by 4, all right, 3 rows and 4 columns, we would say it has an order of 3 by 4. If the rows and columns are equal, the same number of rows and the same number of columns, then we would say that it is a square matrix. So two matrices are equal matrices if they have that same order, and if each element in corresponding positions is the same for each matrix. Okay, so let's talk a little bit about how we determine the order of a matrix. So in matrix A, in the part for A, this matrix has 2 rows, 1, 2 rows, and 1, 2, 3 columns. Therefore, it has an order of 2 by 3, meaning 2 rows and 3 columns. The second one, 1, 2, 3, 4 rows, 2 columns, 4 by 2. The last one is a square matrix, 3 rows, 3 columns, so it's 3 by 3. We always list the number of rows first, the number of columns second. Now we can perform operations with matrices. We can take one matrix and add it to another. We can take one matrix and subtract it from the other. And we denote this as shown in this definition box right here. If A is the matrix A sub ij and B is the matrix B sub ij, then each of them has an order of m by n. Notice the order has to be the same. Then the sum of A plus B is also going to be a matrix that's m by n, and it's just going to be every position in A, we add the corresponding values. So if we were going to look at example 2, if we're going to add these two matrices together, we would add 509 and 510. We would add 509 and 509, etc. You would actually add the two pieces together. And what this example is doing, it's saying it gives the average SAT verbal scores over a time period from 2001 to 2004, and matrix B gives the math score. So it's like the math score plus the verbal. So they want to get the total score. You would add the two components together. So we would add each of the corresponding pieces, 512 plus 514, and the result would go in the exact same position. All right? And when we do that, that 509 plus 510 gave me 1019. All right, if I picked another random spot, 502 plus 504, 1006. The corresponding pieces are just the sum of those pieces. If we were to be subtracting the matrices, we would subtract corresponding pieces in the same manner. There are going to be times with matrices where we are going to want to multiply a matrix by some type of scalar value. All right. So real numbers, they're considered scalars, and the product of a real number times a matrix is simply each element in the array gets multiplied by that scalar. All right, so here's an example. We have a matrix here. Consumer advocacy group has computed the mean retail prices for brand name products versus generic products in different stores in a major city, and they're shown in the 3x2 matrix. The city has a combined sales tax of 7.25% or 7.25%, and we want to show a matrix or create a matrix that has the price of items with tax included. All right, so essentially all we would do is we would multiply each element in the array by 1.0725. The reason why it's this is because 7.25% as a decimal is that value. And so we would have to multiply by 1.0725 because we want to add in that additional tax percentage. All right, so when we do that, we're multiplying by that 1.0725 and we end up getting the final result. So 3.97 times 1.0725 gives me 4.26, etc. You're just multiplying each element by the scalar separately. When we are going to try to multiply two matrices together, it's a little bit more complicated than multiplying by a scalar or the addition or the subtraction. All right, so there are a couple key things that must be true first. First off, matrix A needs to be an M by R matrix, and B would need to be R by N. What this means is that the number of columns in A has to match the number of rows in B. All right? So the number of columns in the first matrix has to match the number of rows in the second. If that's not the case, then we won't be able to determine the product of two matrices. All right? Once we do that, then we determine that the product of A times B, all right, first off, is going to have an order of M by N, meaning it will have the number of rows of A and the number of columns of B, not the number that matches, right? It's going to be the rows of A, columns of B, all right? Whereas it was the columns of A and the rows of B had to match. So we create an M by N matrix where each element in the new matrix is going to be A sub I1 times B sub 1j plus A sub I2 times B sub 2j, etc. And that seems to be a little bit confusing, so we'll actually have to do this kind of step by step and just kind of see how it works out. So let's take a look at this very simple example. First off, we have a 1 by 3 matrix and a 3 by 1 matrix. All right. When I multiply these two matrices together, notice I have the 3 and the 3, they match. And so my resulting matrix is just going to have an order of 1 by 1. It's going to be rows of A, columns of B. So it's just going to be a 1 by 1 matrix. Now we're going to take the 1 and we're going to multiply it times the 4. All right. Then we're going to take the 2, we're going to multiply it times the 5. So the 2 goes with the 5, the 3 goes with the 6, etc. We're going to take and we're going to do all of those pieces of multiplication, and then we're going to add all of the results. So 1 times 4 plus 2 times 5 plus 3 times 6, which gives me 32, and 32 is going to be in a 1 by 1 matrix. All right. That seems very complicated. All right, and when we look at it in larger matrices where we end up with a resulting matrix that is larger than a 1 by 1, it may seem pretty confusing. And we're just going to have to take a few attempts, go through a few of these, just to make sure we have a solid understanding of how multiplying matrices works. So let's go ahead and do a bit of practice. So we're going to try and find the product in two different cases. In the first one, we have a 2 by 3 matrix times a 3 by 2 matrix. These we can multiply because the 3's are the same. It's going to yield a 2 by 2 matrix, all right? And we're not going to compute what's inside just yet. The second one, we have a 2 by 3, and we're trying to multiply it by a 2 by 2. Because the inner pieces, the columns for A does not equal the rows from B, we cannot multiply. So there's undefined. There's no matrix here. It's not possible to multiply. All right, so the first thing we want to do, we want to check, can we multiply them? So really, we're only going to find the answer to A. All right, so let's take a look at the solution here. Now, in A, we're going to take the first row, times the first column, and that's going to give me the element in the first position. All right, so remember, we're going to get a resulting array that is just 2 by 2. So it's going to be 2 times 1 is 2, 1 times 0 is 0, so we're at 2 plus 0, and then negative 3 times 1 is plus a negative 3. When I add all that together, we get negative 1. So negative 1 goes in the top left column. Second, we're now going to multiply. The first row again times the second column. And that'll give me what's in the position 1, 2. First row, second column. So you can kind of think about it this way. First row, first column gives me position 1, 1. First row times second column gives me position 1, 2. So 2 times negative 4 plus 1 times 2 plus negative 3 times 0. All right, so it's negative 8 plus 2 is negative 6 plus 0 just gives me negative 6. So we would get a negative 6 in the next position. I'm intentionally using different colors here when I circle just so you can see exactly what's being multiplied each time. So now we're going to do second row times first column. And that's going to give me what's in the position 2, 1, or in the bottom left corner. So 0 times 1 is 0, plus 1 times 0 is 0, plus 2 times 1 is 2. So I will get a 2 in the bottom left corner. The last one, all right, is going to be that second row times the second column. And we're going to get 0 times negative 4 is 0, plus 1 times 2 is 2. 2 times 0 is 0. 0 plus 2 plus 0 is just 2. So our final resulting matrix is going to be this matrix shown here, which, as we can see, is what we got over there as well. And I think it's important to note that what we're doing, in order to get something in a position, we're multiplying an entire row times an entire column. All right, and we just do that one at a time. It ends up being a lot of steps to get one resulting matrix, but that's how you do it. You have to break it down into all the small pieces and just do them one piece at a time. All right, so now when will we actually use matrix operations? All right, for example, when do we use matrix multiplication? Well, in the real world, we can actually do this. Here are a couple of examples. In the first example that we're going to look at, we have a florist, and they make different flower arrangements for Mother's Day. We just label them as 1, 2, and 3, and we put those in the columns, and they involve either roses, carnations, or lilies. All right. So the number in the matrix shows the number of each type of flower used in each arrangement, meaning in arrangement 1, it uses 5 roses, 6 carnations, and 4 lilies. In arrangement 2, we have 8 roses, 6 carnations, 3 lilies. And in arrangement 3, we have 7 roses, 7 carnations, and 3 lilies. All right, so the florist can buy their flowers from 2 different wholesalers, wholesaler 1 or wholesaler 2, but wants to give all of his business to one or the other. They don't want to have to kind of parse it out and buy some roses from one or some carnations from one, etc. Now, if we look at this, wholesaler 1 sells their roses for cheaper than wholesaler 2, or for slightly more expensive. The carnations, on the other hand, are a little bit cheaper, and the lilies are a little bit cheaper. All right? So now, the flower shop wants to know, well, which one is the one that they should, do their business with. All right, given that the costs for the flowers are different amounts. You might be asked to, say, construct a matrix showing the cost of making each of the 3 flower arrangements from the flowers supplied by the 2 wholesalers. So what is the cost for roses in number 1? Or what is the cost of arrangement 1 from wholesaler 1? What is the cost of arrangement 2 from wholesaler 2, etc.? All right? We could actually go about doing this simply by multiplying the 2 matrices. All right? So for example, we'd want to kind of label it slightly different, and we're going to kind of change it a little bit because we want to make sure that when we go to do our multiplication problem, that we're multiplying to get the correct values, etc. So when we do this, all right, we would want to multiply having the rose, carnations, lilies as our columns in the first matrix, all right, because we need the columns to match the rows of the next, all right. That's the key. The columns of the first matrix has to match the rows of the second matrix, right? So we can kind of turn our matrix, kind of change the way it's laid out, but that's fine. But then based on matrix multiplication, we would multiply all the stuff for arrangement 1 times the costs from wholesaler 1 to get the price for wholesaler 1, etc. And as we go through and we do all the multiplication, we find the cost for each arrangement based on each wholesaler. So arrangement 1 at wholesaler 1 cost them $18.40. Arrangement 2 is $21.60 and arrangement 3 is $21.05. Notice all 3 arrangements from wholesaler 2 end up being slightly cheaper. So as the owner of the flower shop, I'd say, oh, I want to buy from wholesaler 2 because all of my arrangements will be cheaper to make. And if they're cheaper to make, then you're going to increase your overall profits. So far in this lesson, we went ahead and we went through and we looked at what are matrices. We looked at the operations with matrices. We have not jumped yet into identity and inverses. We're actually going to do that in our next video. But we did go through that first part. So at this point, you should be able to perform those matrix operations. All right. We've met that first objective, and that's what you should be able to do. In our next lesson, we're going to continue on with matrices, and we're going to hit that identity matrix and look at inverses and determinants.